Hi everyone, I'm Damian Dobrowolski, and this is my presentation on quantum computing applications for machine learning. Quantum machine learning, this is the application of quantum computing to AI neural networks. First of all, what is machine learning? They're AI systems that are built from algorithms, and they use data to perform actions. And what they do with this data is they analyze it for patterns, and they can infer things about it. And by doing this over and over again, they improve and learn, essentially, which is why it's called machine learning. And there are different types, supervised, unsupervised, and reinforcement. And supervised is when the data is actually labeled by humans. So the machine knows what the data is and what the output should be. And so it's able to account for that. Then there's unsupervised, where it's just raw data and the machine um, just groups it together based on different patterns and things like that. And then there's reinforcement, which is where there is a reward given for correct interpretations, and then the program is geared to maximize that reward. So it will keep trying to get that reward and to create the kind of situation where the desirable outcome occurs. And so all of these things have very demanding hardware, software, and processing requirements, using huge data sets and advanced algorithms and lots of linear algebra to um, get these outcomes from these networks. So, can quantum computing improve machine learning? So, for specialized computing tasks, for instance, factoring large numbers, we know that quantum computing is much faster, but we're not sure about the applications for traditional machine learning. And some think that it could spot more patterns in data because of enhanced computational power, but this has yet to be kind of proven. However, it is quite promising for quantum problems, which are not classical, and we'll look at that later. And so, using Hilbert spaces, which is a special mathematical structure which kind of describes quantum mechanics in nature, um, using them, we can describe complex data structures with far fewer parameters, which basically means that um, quantum computing and quantum problems, it can capture complex patterns much better, and it's less complicated and less expensive. So this is an application that could be promising. And basically, there are three steps of quantum computing that we have to understand to assess this question, which are initialization, operations or computation, and interpretation. So theoretically, quantum algorithms would make machine learning much more efficient because one of the major parts of machine learning is solving algorithms, for instance, solving large sets of linear equations. And so since they're exponentially faster at doing these things, you would think that they would be way better for machine learning. But let's take a look at the three steps and then see where some problems lie. So the first is initialization, where all the qubits are placed into a collective entangled state, which you can see here in the image on the very left. We're in the prepare quantum dataset portion. Then the second is operations, or the computation part, where these quantum algorithms would be much faster. And this involves basically the quantum equivalent of what are logical operations on bits. So things that we've been doing this semester, for instance. And that's part of like evaluating the quantum model. You can see there in the middle of the image in the blue area. Um, and then third is interpretation. And that's where the state of the qubits is measured to generate an output, which is on the right side of the image in averaging or sampling, and then evaluating the model. So the problem that is found here is that the first and the third steps, so initialization and interpretation, they're extremely slow. And if the second step is much faster because of increased computation, which allows the algorithms to be computed much faster, it doesn't matter because these first and third steps are so slow that it won't make a significant impact on the overall speed of the process. Because in the first step, the classical data has to be translated to a quantum version, and this is very inefficient and slow. And then in the third step, because of the superposition of the qubits of being in a state in between 0 and 1, basically what that means is they have a probability of either going to 0 or to 1. So in the image here, you can see there's a 0, um, or it's a qubit, and essentially there's a 70% chance that it will be realized as a 0 and a 30% chance of it being a 1. And then so from each of those, there's then another probability that um, the next one will be a 0 and a 1, and so on. And so essentially, when you're doing the interpretation or the readout of the quantum data, the superposition is translated to a 0 or a 1, but this process is essentially has an element of randomness because it's a probability. And so to get a true reading of it, it needs to be repeated many, many times, so that the probabilities kind of accurately represent what the qubits are actually representing. So this also makes it not efficient for classical data, because the third step, just like the first step, is very inefficient and takes a long time. So what could be the solution here? And there's a new novel kind of technique called quantum sensing, which basically answers the question, what if we start with quantum data? If the classical data is inefficient because we have to convert it and then interpret it, what if we just start with quantum data? And so um, traditional quantum physics measures quantum phenomena with classical instruments, which basically are living in the macroscopic world. They're not in the quantum realm. Um, and so quantum sensing says, what if we measure these quantum states instead of with these classical instruments with quantum instruments? And so there are quantum sensors and other tools used to measure these quantum states. And this allows the quantum states to be loaded onto qubits directly. And so it bypasses the first step of having to translate all the classical data into quantum, and then again at the end interpreting all the quantum data um, as classical ones and zeros. And so what this means is that there will be no interference from classical systems in our three-step process, um, which, as we've seen, makes the whole thing very inefficient and not feasible for machine learning. And that would mean we could have very efficient machine learning algorithms using quantum measurements, um, and removing the classical system um, involvement in the process. And so the conclusion basically is that it's just too early to tell if these things will actually be realized in terms of the quantum sensor technology, and in general, if the quantum data can be used effectively and the quantum problems can be applied to machine learning instead of the classical data. And so if quantum sensing is effective, then we will bypass the inefficient first and third steps of the quantum computing process and have great improvements in machine learning, which will allow us to be have much faster algorithms and solving these sets of linear equations that makes machine learning so computationally intensive. And also maybe we'll be able to extract more patterns from the data and understand different things that we didn't find before, to basically, as an outcome, have vastly more nuanced and varied kind of interpretations of the data. Um, However, the classical data and measurement, combined with quantum computing, might not be feasible for machine learning at all because of these inefficiencies that we've seen in the steps. And so, if quantum sensing isn't able to kind of eliminate those inefficiencies by keeping everything in the quantum realm, um, then quantum computing might not be able to do anything for machine learning. And here's some of my research. And yep, thank you so much.